Okay, here I want to continue with the energy balance. And the main topic of this lecture is to solve an example of the head energy equation. So still I am the same section, which is 5.6, the energy analysis of steady flows. Let me just go through this example with you, which is about pumping power and frictional heating in a pump. So I will read it and I will try to sketch the problem with you other than the sketch in the book. So let us go through it. So the pump of a water distribution system is powered by a 15 kilowatt electric motor whose efficiency is 90%. So what I'm going to do, I'm going to draw as usual something like this. So let me assume that this is my motor. This is WEN, and here is W, let us say W shaft, or W if you want, W pump. Okay, and what else? So this is the energy direction from the electricity to the motor to the shaft to the pump, and from the pump to the fluid that is going to be raised, let us say from E mechanical N to E mechanical, E to mechanical out. This is the summary of the problem. So it's powered by 15 kilowatt electrical motor. So I can say that W, and here let me just change the color. Let us say this is 15 kilowatt, okay, which is WEN, which is electricity N, and the motor whose efficiency is 90%. So here the efficiency of the motor is 0.9, 90%. The water flow rate through the pump is 50 liters per second. So the water flow rate, so I will just write it here, m dot is equal to, I believe, 50 liters per second. The diameters of the inlet and the outlet pipes are the same. So the water is going, let us say, I don't know, from here to here, and here D1, and here D2, and D1 is equal to D2. Okay, which means A1 is equal to A2. I mean the diameter. Let me go back to this. So if this is, for example, if this is A1, then this is A2, which corresponds to, this is D1, and this one here is D2. So the diameters are the same. And the elevation difference across the pump is negligible, which means from, let us say, from here, from this point to this point, delta Z is negligible. So here I can say that delta Z is almost equal to 0, negligible, okay? Because I'm looking the height of the pump. What is next? If the absolute pressure at the inlet and the outlets of the pump are measured to be 100 kilopascal and 300 kilopascal, which means here at point 1, let us say this is point 1, P1 is equal to 100 kilopascal, and here if this is point 2, P2 is equal to 300 kilopascal. Now it is obvious. It is obvious here. It is better than my sketch. Okay, so it is 100 kilopascal here, 300 kilopascal there. So this is a good representation of the problem. As you can see, you can present it this way, easy sketch for a guy like me that is bad in drawing. So I will be happy with if you do this for me, and this is how professional one drawn in the book. So what's required here? So number one, determine the mechanical efficiency of the pump. Number two, the temperature rise of water as it flows through the pump due to the mechanical inefficiency. We have done something similar to this, the temperature rise, if you remember, when we talked about the efficiency and the losses. So the first thing is the mechanical efficiency of the pump. This is the first thing. So I have to look at the pump, which is this part, and we know that the efficiency of the pump is equal to what? Is whatever the power output, which is delta E. So it is delta E mechanical of the fluid divided by what I'm inputting, which is this, which is W pump. Okay. So this is in a nutshell, and let us go through the solution in detail. Let me go through the slides. Okay. So as I told you in the homework, I want you to show me step by step. So this is like the description of the problem. The pressure across the pump are measured. Okay, the pressures across the pump are measured. The mechanical efficiency of the pump and the temperature rise of water are to be determined. This is what's required. When I ask you, tell me what's required. So I want the efficiency and the temperature rise. Now, those are the assumptions also that you have to write in these, in the assignments. So usually the flow is steady and incompressible because, these are the assumptions upon which we derive the energy balance equation. The pump is driven by external motor so that the heat generated by the motor is dissipated to the atmosphere. So here he is just signaling for the adiabatic condition. This is, we might use it later. This is important. The elevation difference between the inlet and the outlet of the pump is negligible. Z1 is equal to Z2. Here you might say, oh, is this an assumption or is this information is given? So actually, even though it is said there, you have to confirm it. Sometimes it is not mentioned in the problem. So also you have to say it as an assumption. And here the inlet and the outlet diameters are the same, and thus the average inlet and outlet velocities are equal. V1 is equal to V2. Since D1 is equal to D2, so A1 is equal to A2, but you know that this is steady flow, so M1 is equal to M2. And you know M1 is equal to ρ1, A1 V1 is equal to ρ2, A2 V2. Okay, so I can cancel ρ1 with ρ2. Okay, since it is incompressible, the same areas. So from here I can get V1 is equal to V2, which is this conclusion. And then there is number 5, which is the kinetic energy correction factors are equal. So I haven't discussed this yet. I will discuss it in the next lecture. For the time being, just keep it in mind. And then for the properties and constants, also I told you about it. So we take the density of water to be 1 kilogram per liter or 1000 kilogram per meter cube. And for the second part, which is for the temperature rise, you will need the specific heat to be this much, 4.18 kilojoule per kilogram degree centigrade. So this here, what's required, assumptions, properties and constants. You sketch it, you have to sketch it, and as I always tell you, so we sketched it, and now we are ready to solve the problem. Analysis is the solution or the calculation. So the first thing that was done is to calculate the mass flow rate of the water through the pump. So mass flow rate is equal density times volumetric flow rate. This is the density, this is the volumetric flow rate, and this is the mass flow rate, which is 50 kilograms per second. The second thing is to calculate the W pump shaft, or W pump as we called it. Okay, if you remember, which is this thing here, W pump. Okay, for W pump, what have we done? The motor draws 15 kilowatt of power and 90% efficient. So here is 15 kilowatt. I believe efficiency is 90%. So what will happen? Thus, the mechanical shaft power delivered to the pump is this. So what we have done here is the efficiency of the motor, which is this, equal the output, which is this, divided by the input, which is this. And by just rearrangement, we rearrange this. So W pump shaft, which is this one, is equal to efficiency times the electrical energy in equal to 0.9 times 15 kilowatt. This is 0.9, this is 15, and we got this to be 13.5 kilowatt. So this is the shaft power of the pump, 13.5 kilowatt. Now the next step is to determine the mechanical efficiency of the pump. We need to know the increase the mechanical energy of the fluid as it flows through the pump. So this is the mechanical energy increase of the fluid. So you know that the mechanical energy of the fluid equal mechanical out minus mechanical in, and then we write the full details. But you know that, for example, V1 is the same as V2. You know that Z1 and Z2, the difference is negligible. So we are left with just this term, m dot P2 minus P1 over rho. This is the mass flow rate. And here you have the difference in the pressures. And finally, we get this to be delta E mechanical of the fluid, which is equal to what? Which is equal to here, W pump useful. And the efficiency of the pump is equal to W pump useful divided by W pump shaft. And this is equal to this, and this is what we just calculated. And finally, when we substitute the numbers, we got the efficiency of the pump to be 74.1%. What's next? Next is to find the energy or the temperature rise. So first of all, we know that we have lost 3.5 kilowatt. You can go through this because the input was 13.5, if you remember. So again, let me just show you the things here. So here was 15 kilowatt electrical energy in. Because this motor is not 100% efficient, we got out of the 13.5 kilowatt. And because the pump is not 100% efficient, we got out of this just 10 kilowatt. So what happened here? We lost 3.5 kilowatts, and this 3.5 kilowatts converted into a temperature rise. Okay, so the temperature rise of water due to this mechanical inefficiency in the pump is determined from the thermal energy balance. So E mechanical loss is equal M times delta U, which is MC delta T. Okay, and when we solve for delta T, so delta T is equal to the 3.5 kilowatt, which is the mechanical loss, divided by MC, which is this. And finally, we got the temperature rise to be small, to be 0.017 degrees centigrade, which is very small as it flows through the pump. So actually, this wasn't an example, as I told you at the beginning of the head, but the next example for sure it will be for the head equation.